Polar Satellite Launch Vehicle, PSLV. The Polar Satellite Launch Vehicle, PSLV, is an expendable medium-lift launch vehicle, MLV, designed and operated by the Indian Space Research Organisation, ISRO. It was developed to allow India to launch its Indian Remote Sensing, IRS, satellites into Sun-synchronous orbits, SSO, a service that was, until the advent of the PSLV in September 1993, only commercially available from Russia. PSLV can also launch small-size satellites into Geostationary Transfer Orbit, GTO. Some notable payloads launched by PSLV include India's first lunar probe Chandrayaan-1, India's first interplanetary mission, Mars Orbiter mission, unofficially known as Mangalyaan, India's first space observatory, AstroSat-1, and India's first solar mission, Aditya-L1. PSLV has gained credibility as a leading provider of rideshare services for small satellites, owing to its numerous multi-satellite deployment campaigns with auxiliary payloads, usually ride-sharing along with an Indian primary payload. As of June 2022, PSLV has launched 345 foreign satellites from 36 countries. Most notable among these was the launch of PSLV-C-37 on February 15, 2017, successfully deploying 104 satellites in sun-synchronous orbit, tripling the previous record held by Russia for the highest number of satellites sent to space on a single launch, until January 24, 2021, when SpaceX launched the Transporter-1 mission on a Falcon 9 Block 5 rocket carrying 143 satellites into orbit. Payloads can be integrated in tandem configuration employing a dual launch adapter, DLA. Smaller payloads are also placed on equipment deck in customized payload adapters. Studies by the PSLV Planning Group under Dr. Suryanarayanan Srinivasan to develop a vehicle capable of delivering a 600 kg, 1,323 pounds, payload to a 550 km, 342 miles, sun-synchronous orbit from Sriharikota Range, Shar, began in 1978. Among 35 proposed configurations, 4 were picked. By November 1980, a vehicle configuration with 2 strap-ons on a core booster, S-80, with 80 metric tons, 176,370 pounds, solid propellant loading each, a liquid stage with 30 metric tons, 66,139 pounds, propellant load, L-30, and an upper stage called the perigee-apogee system, PAS, was being considered. About a year later, an important change was made, with the solid fourth stage being substituted by a liquid stage. This change was considered necessary since the accuracy with which the IRS satellites had to be put into orbit, within 15 kilometers, 9.32 miles, in terms of orbital height and within 0.1 degrees of the desired orbital inclination, could not be achieved with a solid stage. By 1981, confidence grew in Indian remote sensing spacecraft development with the launch of Bhaskara-1, and the PSLV project objectives were upgraded to have the vehicle deliver a 1,000 kg, 2,205 pounds, payload into a 900 km, 559 miles, SSO. As technology transfer of Viking rocket engine firmed up, a new lighter configuration with the inclusion of a liquid-powered stage was selected. Funding was approved in July 1982 for the finalized design, employing a single large S-125 solid core as first stage with 6.9 metric tons, 19,842 pounds, strap-ons, S-9, derived from the Satellite Launch Vehicle 3, SLV-3, first stage, liquid-fueled second stage, L-33, and 2 solid upper stages, S-7 and S-2. This PSLV configuration needed further improvement to meet the orbital injection accuracy requirements of IRS satellites, and hence, the solid terminal stage, S2, was replaced with a pressure-fed liquid-fueled stage L1.8 or LUS, liquid upper stage, powered by twin engines derived from roll control engines of the first stage. Apart from increasing precision, liquid upper stage also absorbed any deviation in performance of solid third stage. The final configuration of PSLV-D1 rocket to fly in 1993 was, first stage, 6 times S9 plus S125, second stage, L37.5, third stage, S7, fourth stage, L2. The Inertial Navigation Systems, INS, Also, inertial guidance system, inertial instrument, are developed by ISRO Inertial Systems Unit, ISU, at Tiruvananthapuram city, also known as Trivandrum. The liquid propulsion for the second and fourth stages of the PSLV as well as the reaction control systems, RCS, are developed by the Liquid Propulsion Systems Center, LPSC, at Valiamala town near Tiruvananthapuram, Kerala. The solid propellant motors are processed at Satish Dhawan Space Center, SDSC, formerly Sriharikota Range, SHAR, at Sriharikota, Andhra Pradesh, which also carries out launch operations. The aerodynamic characterization research was conducted at the National Aerospace Laboratories, NAL, 1.2 meter, 4 foot, trisonic wind tunnel facility. The PSLV was first launched on September 20, 1993. The first and second stages performed as expected, but an attitude control problem led to the collision of the second and third stages at separation, and the payload, IRS-1E, failed to reach orbit. After this initial setback, the PSLV successfully completed its second mission, IRS-P2, on October 15, 1994. The fourth launch of PSLV suffered a partial failure on September 29, 1997, leaving its payload, IRS-1D, in a lower-than-planned orbit. In November 2014, the PSLV had launched 34 times with no further failures. Although launch number 41 on August 31, 2017 with PSLV-XL C-39, IRNSS-1H, was unsuccessful. PSLV launch vehicle continues to support Indian and foreign satellite launches especially for low Earth orbit, LEO, satellites. It has undergone several improvements with each subsequent version, especially those involving thrust, efficiency as well as weight. On November 5, 2013, it was used to launch the Mars Orbiter mission, MOM, India's first interplanetary probe. In June 2018, the Union Cabinet approved 6,131 crore Indian rupees, abbreviated CR, denotes the quantity 10 million rupees, equivalent to 72 billion Indian rupees or $850 million in 2023, for 30 operational flights of the PSLV scheduled to take place between 2019 and 2024. ISRO is working towards handing over the production and operation of PSLV to private industry through a so-called joint venture. On August 16, 2019, New Space India Limited, NSAL, issued an invitation to tender for manufacturing PSLV entirely by private industries. On September 5, 2022, New Space India Limited signed a contract with Hindustan Aeronautics Limited, HAL, and Larsen & Toubro, L&T, led conglomerate for the production of 5 PSLV-XL launch vehicles after they won competitive bidding. Under this contract, they have to deliver their first PSLV-XL within 24 months and the remaining 4 vehicles every 6 months. The PSLV has 4 stages, using solid and liquid propulsion systems alternately. The first stage, one of the largest solid rocket boosters, SRBs, in the world, carries 138 metric tons, 136 long tons or 152 short tons, of hydroxyl-terminated polybutadiene-bound, HTPB, propellant and develops a maximum thrust of about 4,800 kilonewtons, 1,100,000 pounds force. The 2.8 meters, 9 feet 2 inches, diameter motor case is made of maraging steel and has an empty mass of 30,200 kilograms, 66,600 pounds. Pitch and yaw control during first stage flight is provided by the secondary injection thrust vector control, SITVC, system, which injects an aqueous solution of strontium perchlorate into the S-139 exhaust divergent from a ring of 24 injection ports to produce asymmetric thrust. The solution is stored in 2 cylindrical aluminium tanks strapped to the core solid rocket motor and pressurized with nitrogen. Underneath these 2 SITVC tanks, roll control thruster, RCT, modules with small bipropellant, MMH-MON, liquid engine are also attached. On the PSLV-G and PSLV-XL, first stage thrust is augmented by 6 strap-on solid boosters. 4 boosters are ground-lit and the remaining 2 ignite 25 seconds after launch. The solid boosters carry 9 metric tons, 8.9 long tons, 9.9 short tons, or 12 metric tons, 12 long tons, 13 short tons, for PSLV-XL configuration, propellant and produce 510 kilonewtons, 110,000 pounds force, and 719 kilonewtons, 162,000 pounds force, thrust respectively. 2 strap-on boosters are equipped with a SITVC system for additional attitude control. The PSLV-CA variant uses no strap-on boosters. First stage separation is aided by 4 pairs of retrorockets installed on interstage 1-2L. During staging, these 8 rockets help push away the spent stage away from second stage. The second stage is powered by a single Vickers engine and carries 41.5 metric tons, 40.8 long tons, 45.7 short tons, of Earth-storable liquid propellant, unsymmetrical dimethylhydrazine, UDMH, as fuel and nitrogen tetroxide, N2O4, as oxidizer in 2 tanks separated by a common bulkhead. It generates a maximum thrust of 800 kilonewtons, 180,000 pounds force. The engine is gimbaled, plus or minus 4 degrees, in 2 planes to provide pitch and yaw control by 2 actuators, while roll control is provided by a hot gas reaction control motor, HRCM, that ejects hot gases diverted from gas generator of Vickers engine. On interstage 1-2U of PS2, there are 2 pairs of ullage rockets to maintain positive acceleration during PS1-PS2 staging and also 2 pairs of retrorockets to help push away spent stage during PS2-PS3 staging. Second stage also carries some quantity of water in a toroidal tank at its bottom. Water spray is used to cool hot gases from Vickers gas generator to about 600 degrees Celsius 1112 degrees Fahrenheit before entering turbopump. Propellant and water tanks of second stage are pressurized by helium. The third stage uses 7.6 metric tons, 7.5 long tons, 8.4 short tons, of HTPB solid propellant and produces a maximum thrust of 250 kilonewtons, 56,000 pounds force. Its burn duration is 113.5 seconds. It has a strong Kevlar polyamide fiber case and a submerged nozzle equipped with a flex-bearing seal gimbaled nozzle with plus or minus 2 degrees thrust vector for pitch and yaw control. Roll control is provided by the 4th stage reaction control system, RCS, during thrust phase as well as during combined coasting phase under which burnt-out PS3 remains attached to PS4. The 4th stage, PS4, is powered by regeneratively cooled twin engines, burning monomethylhydrazine, MMH, and mixed oxides of nitrogen, MON. Each pressure-fed engine generates 7.4 kilonewtons, 1,700 pounds force, thrust and is gimbaled, plus or minus 3 degrees, to provide pitch, yaw, and roll control during powered flight. Coast phase attitude control is provided by 650 newtons, 11.24 pounds force, reaction control system thrusters. The stage is pressurized by helium and carries 1,600 kilograms, 3,500 pounds, to 2,500 kilograms, 5,500 pounds, of propellant depending on the mission requirements. The 4th stage has 3 variants L1.6, L2.0 and L2.5 based on propellant tank capacity. On PSLV-C-29, Telios 1, mission, the 4th stage demonstrated reignition capability for the first time, which was used in many subsequent flights to deploy payloads in multiple orbits on a single campaign. As a space debris mitigation measure, PSLV 4th stage gets passivated by venting pressurant and propellant vapor after achieving main mission objectives. Such passivation prevents any unintentional fragmentation or explosion due to stored internal energy. The niobium alloy nozzle used on twin engines of 4th stage is expected to be replaced by lighter, silicon carbide-coated carbon nozzle divergent. The new nozzle was hot tested at facilities of the ISRO Propulsion Complex, IPRC, Mahendragiri in March and April 2024. This substitution should increase payload capacity of PSLV by 15 kilograms, 33 pounds. ISRO also replaced imported columbium, C103, materials in the engine nozzle divergent with stellite, KC20WN, which resulted in cost savings of 90%. The newly modified engines were tested at IPRC in April 2025. ISRO successfully completed 665-second hot test of 3D printed PS4 engine, produced by Wipro 3D through selective laser melting. A total of 19 weld joints were eliminated through this process while engine's 14 components were reduced to one piece. It saved 60% of the production time and drastically decreased the number of raw materials used per engine, from 565 kilograms, 1,245.6 pounds, to 13.7 kilograms, 30 pounds, of metal powder. The Reusable Launch Vehicle Technology Demonstration, RLVTD, program is a prototype spaceplane project currently being processed by ISRO. It is planned to use a Geosynchronous Satellite Launch Vehicle, PSLV, modified by replacing its cryogenic upper stage, CUS, with the PS4 as the RLV would not require the excess thrust created by the CUS. Payload fairing of PSLV, also referred as its heat shield, consists of a conical upper section with spherical nose cap, a cylindrical middle section and a lower boat tail section. Weighing 1,182 kilograms, 2,606 pounds, it has 3.2 meter, 10.5 foot, diameter and 8.3 meter, 27 foot, height. It has isogrid construction and is made out of 7075 aluminum alloy, AA7075, with a 3 mm, 0.118 inches, thick steel nose cap. The two halves of fairing are separated using a pyrotechnic device-based jettisoning system consisting of horizontal and lateral separation mechanisms. To protect the spacecraft from damage due to excessive acoustic loads during launch, the heat shield interior is lined with acoustic blankets. ISRO has envisaged a number of variants of PSLV to cater to different mission requirements. There are currently two operational versions of the PSLV, the core alone, PSLV-CA, without strap-on motors, and the PSLV-XL version, with 6 extended length, XL, strap-on motors carrying 12 metric tons, 12 long tons, 13 short tons, of HTPB-based propellant each. These configurations provide wide variations in payload capabilities up to 3,800 kilograms, 8,400 pounds, in LEO and 1,800 kilograms, 4,000 pounds, in Sun-synchronous orbit. The standard or generic version of the PSLV, PSLV-G had 4 stages using solid and liquid propulsion systems alternately and 6 strap-on motors, PSOM or S9, with 9 metric tons, 8.9 long tons, 9.9 short tons, propellant loading. PSLV-G rocket had the capability to launch 1,678 kilograms, 3,699 pounds, to 622 kilometers, 386 miles, into Sun-synchronous orbit. PSLV-C-35 was the last operational launch of PSLV-G before its discontinuation. The PSLV-CA, CA meaning, core alone, model premiered on April 23, 2007. The CA model does not include the 6 strap-on boosters used by the PSLV standard variant, but 2 SITVC tanks with roll control thruster modules are still attached to the side of the first stage with addition of 2 cylindrical aerodynamic stabilizers. The 4th stage of the CA variant has 400 kilograms, 880 pounds, less propellant when compared to its standard version. PSLV-CA rocket currently has capability to launch 1,100 kilograms, 2,400 pounds, to 622 kilometers, 386 miles, Sun-synchronous orbit. PSLV-XL is the upgraded version of Polar Satellite Launch Vehicle in its standard configuration, boosted by more powerful, stretched 6 strap-on boosters with 12 metric tons, 12 long tons, 13 short tons, propellant load. Weighing 320 metric tons, 310 long tons, 350 short tons, at liftoff, the vehicle uses larger strap-on motors, PSOM-XL or S12, to achieve higher payload capability. On December 29, 2005, ISRO successfully tested an improved version of the strap-on booster for the PSLV. The first use of PSLV-XL was the launch of Chandrayaan-1 by PSLV-C11. The payload capability for this variant is 1,800 kilograms, 4,000 pounds, to Sun-synchronous orbit. PSLV-DL variant has only 2 strap-on boosters with 12 metric tons, 12 long tons, 13 short tons, propellant load on them. PSLV-C-44 rocket on January 24, 2019 was the first flight to use PSLV-DL variant of Polar Satellite Launch Vehicle. It is capable of launching 1,257 kilograms, 2,771 pounds, to 600 kilometers, 370 miles, Sun-synchronous orbit. PSLV-XL variant has 4 groundlet strap-on boosters, each with 12 metric tons, 12 long tons, 13 short tons, of propellant. PSLV-C-45 on April 1, 2019 was the first flight of PSLV-XL. PSLV-XL rocket has the capacity to launch 1,523 kilograms, 3,358 pounds, to 600 kilometers, 370 miles, Sun-synchronous orbit. PSLV-3S was conceived as a 3-staged version of PSLV with its 6 strap-on boosters and second liquid stage removed. The total lift-off mass of PSLV-3S was expected to be 175 metric tons, 385,809 pounds, with capacity to place 500 kilograms, 1,102 pounds, in 550 kilometers, 342 miles, low Earth orbit. The PS-1 ignites at T+0 providing 4,846 kilonewtons, 1,089,424 pounds force, of thrust. Within T+1 second, 4 out of the 6 boosters ignite on ground, each producing 703 kilonewtons, 158,041 pounds force, of thrust. 7,658 kilonewtons, 1,721,587 pounds force, of total thrust is produced by the combined propulsion of the PS-0 strap-on motors, SOMs, and the PS-1. At around T+23-26 seconds, the remaining 2 unlit boosters are airlit, bringing the rocket at its maximum thrust capacity. At T+1 minute 10 seconds, the first 4 groundlit SOMs have depleted its propellant and now separates and falls down to the ocean. The remaining 2 SOMs and the PS-1 continue to burn. At T+1 minute 35 seconds, the remaining 2 SOMs complete its 70 seconds burn and separate, leaving the rocket in a core-alone configuration. At T+1 minute 50 seconds, the PS-1 has completed its 110-second burn and it separates and the VICUS engine inside the PS-2 ignites. The second stage burns for around 130 seconds and around T+4 minutes, the second stage shuts off and separates. The third stage, which is a solid rocket booster, and burns 80 seconds and then coasts for the remainder of time and around T+8-10 minutes, it separates and the fourth stage ignites to give the rocket a final push into the orbit. This fourth stage burn is highly variable and depends on the mass and number of payloads and is usually around 500 seconds long. The fourth stage may shut off around T+16-18 minutes followed by the payload deployment. As of May 18, 2025, the PSLV rocket has made 62 launches, with 58 successfully reaching their planned orbits, 3 outright failures and 1 partial failure, yielding a success rate of 94%, or 95% including the partial failure. All launches have occurred from the Satish Dhawan Space Center, SDSC, known before 2002 as the Sriharikota Range, SHAR.